Welcome to section 3.5, talking about derivatives of trigonometric functions. And this is the last section in this unit, and this unit has been a combination of common differentiation tools that we're going to need to use, along with big applications, things like position, velocity, acceleration, and talking about rates of change. And this last section is going to take those rules and applications that we've already talked about and apply them to the trigonometric functions. So the first things that we're going to look at are our sine and cosine functions. And these two graphs should look pretty familiar to us. And thinking about the title of this section, you already know that we're going to be talking about derivatives for these types of functions. Let's start with sine. If I wanted to talk about the derivative of the sine function, well, I'm going to take something that we've already talked about regarding derivatives, and I'm going to find a couple spots where I know the derivative of the sine function. And that will be any of these spots where the function has a maximum or minimum, where it flattens out, where the slope is 0. Because I can use those to help me guide the drawing of my derivative function. All of those will be zeros, will be roots for the derivative. In between those spots, though, I want you to think about what is happening. Let's start with this one over here to this 0 over here. This function is increasing. This should be a spot where that derivative is positive. And when I get to this point right here, what it certainly looks like is this might be a slope of about 1. And in fact, it is. Thinking about the cyclical, the symmetric nature of the sine curve, you might also guess that this spot might have a slope of -1. And it does. And connecting those points, the best way that I could think to do that is with a curve that looks like this. And if that curve is looking familiar to you, well, that's because it looks like the exact function that you see over here on the right. A nice property of the sine curve is that its derivative is the cosine curve. Well, if that's the case, let's think about f of x equals cosine of x, a curve that is exactly the same as the sine curve except shifted. Well, if I look, I can find a couple spots where I know the derivative will be equal to 0. Here's one, and here's one over here. And I can draw those in to start making my f prime function. Notice we've still got the same main spots where we can estimate the slope pretty well. I got a slope of 1 here, a slope of -1, back to a slope of 1. So I can draw in a couple more key points. And connecting them, this does not look too far off from the curve back over here on the left, my sine of x curve, except there's one small difference. It's flipped. And in fact, the derivative of cosine is actually the negative of the sine curve, negative sine of x. And those are the two big derivatives that we need to know to talk about derivatives for any trigonometric function. We need to know that the derivative of sine of x is cosine of x, and that the derivative of cosine of x is negative sine of x. Because if I know those two, then when I think about something like the derivative of tangent of x, well, keep in mind your trig identities, I'm really only thinking about derivative of sine of x divided by cosine of x. Cosecant is actually the derivative of 1 over the sine function, secant is derivative of 1 over the cosine function, and cotangent is derivative of cosine of x divided by sine of x. Knowing these, you can develop all the others using the quotient rule. Using the quotient rule and some simple tricks for simplifying, you will get the other 4 trig derivatives. I can show that in another video in case you want to see the proofs. You could also try to develop them on your own. What I'm going to do is jump straight to the final derivatives. The derivative of tangent x, when written out and simplified, becomes secant squared of x. The derivative of the cosecant function is negative cosecant of x times cotangent of x. The derivative of the secant function is secant of x times tangent of x. And the derivative of the cotangent function is negative cosecant squared of x. And what you need to know are just these. Lock those into memory, and you can deal with any functions that are written as trig functions. In order to help you with that, here are a couple tricks. Again, since the big ones are sine and cosine, you can use the unit circle to help with those. Just recall where sine and cosine are positive and negative around the unit circle. Sine of x is positive along the upper part of the y-axis. Then we have negative cosine. That's where sine is negative, and that's where cosine is positive. And how this works is the derivatives move around clockwise. The derivative of sine of x is cosine of x. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. and derivative of negative cosine brings you back to positive sine of x. Getting the other ones memorized is a little trickier, but not impossible. And again, I've got another helpful trick for you to use with that. And it's going to be cover 1, read 2. What you're going to do is make up a chart that reads like this. Sec, tan, negative, kissa, cot. We have 6 different trig functions listed, and the trick to this is it's really 2 rows. And all you have to do is cover up one of those trig functions, and what remains on its row is its derivative. And so to use this, let's say I wanted to find the derivative of secant x. What I'd do is I would cover up, or I'm just going to cross out one of these secants, and what's left is secant tangent. Secant of my inside function x times tangent of my inside function x. If I wanted to find the derivative of cosecant x, well, I'd cover up one of these cosecants. Let's say this middle one. The important thing on this row is to realize there's always this negative sign hanging out in the front. So derivative of positive cosecant is negative cosecant x cotangent of x. And so even though it may seem like a lot of rules to remember, it won't take too much effort on your part if you can just remember to use the tools that I've given you here. The last big thing that you have to realize, trig functions mean chain rule. You read them as sine of, cosine of. Whatever is inside is a chain that you have to take care of using the chain rule. That's going to be the only really tricky part when dealing with derivatives of trig functions. So let's try to put our derivative rules to use. Find the derivative of the following. F of x equals sine of x plus tangent of x. Well, this is just a sum, so I can go ahead and differentiate these separately. Derivative of the sine function, like we read above, is cosine of x. And now what I'm going to say is times 1. This is an inside function of x, so I want us to always be aware of utilizing the chain rule on our trig functions. Plus, derivative of the tangent of x function, well, that outside tangent function, its derivative is secant squared of whatever's inside times derivative of that inside function, which again is 1. So for one like this, I probably wouldn't normally write it in 2 steps, but this is just to emphasize to you that every trig function is a chain rule.
Let's look at the second problem. Y equals cosine of 3x. So the first thing we should notice is we have an outside function, cosine of the inside, and we have an inside function, which is 3x. So our derivative using the notation dy dx will be derivative of the cosine, which will be negative sine of my inside function 3x times derivative of the inside function 3. The negative and the 3 will become a negative 3 out in front, sine of 3x. Problem number 3. Y equals 3x times cotangent of x squared. First thing we should notice is we have 2 functions being multiplied. We call this our u function 3x, our v function cotangent of x squared. So this has to follow the product rule. So what we'll do for dy dx, we'll do first times derivative of the second. So the first function, which is 3x, times, and on that second function, we're going to automatically think, since it's a trig function, about doing the chain rule with an outside function of cotangent of the inside and an inside function of x squared. And we'll use brackets for this one because it will be a little bit longer. Derivative of the cotangent is negative cosecant squared of whatever our inside function was, which is x squared, times the derivative of x squared, which is 2x. The second function left alone, so cotangent of x squared, times the derivative of the first, and derivative of 3x is 3. And a good final answer could look something like 3 times negative 2x squared cosecant squared of x squared plus cotangent of x squared. And our final example on this side, f of x equals sine squared of 4x. And one thing you might want to do for a problem like this, the reasoning behind this is to make sure that we know that the sine is being squared and not the 4x. Like if I were to write this as sine of 4x squared, we would definitely think the 4x is squared, and that's not the case. But this notation, if it ever confuses you when it comes to derivatives, rewrite your function as sine of 4x quantity squared. because that way it's very easy to see when we go for this derivative, it's going to be a chain rule with an outside of inside squared and an inside of sine of 4x. So following the chain rule, we'll get f prime of x equals the derivative of something squared is 2 times that something, and the inside was sine of 4x, times the derivative of sine of 4x. And for that, we need to also think about that as being a chain rule, because any trig function is a chain rule. This one has outside sine of some inside function, with that inside being 4x. And so the derivative of sine of 4x will be derivative of sine, which is cosine, of the same inside function, times the derivative of the inside function, 4x, which will give us a 4. And putting that all together, moving constant multipliers out to the front, we will get 8 sine of 4x cosine of 4x. Moving along, something that's become pretty normal to us at this point, an evaluation problem. We're going to evaluate the derivative of our function at a given point, and our function is f of theta equals 1 over square root of cotangent of theta. And for this, we're going to go ahead and rewrite this just like we do with any radicals or anytime we work with negative exponents, in this case both. We're going to have cotangent of theta to the negative 1/2 power. And so we can see our chain rule. Outside is inside raised to the negative 1/2, and the inside is cotangent of theta. So taking our derivative, f prime of theta equals negative 1/2 cotangent of theta to the negative 1/2 minus 1, or negative 3/2, times derivative of the inside function. And derivative of cotangent is negative cosecant squared theta. And if we want to, the two negatives that we see are going to become a positive, so we'll have 1/2. Put the easier one out in front, the cosecant squared of theta. Then we have a cotangent theta to the negative 3/2. And now we'll evaluate f prime of pi over 2, which will be 1/2 cosecant squared of pi over 2 times cotangent of pi over 2 to the negative 3/2. Now cosecant is defined at pi over 2, and cotangent of pi over 2 is equal to 0. So that 0 is going to override everything, and we will get that f prime of pi over 2 equals 0. Okay, and back to one more round of tangent and normal line problems. Remember, the process starts off entirely the same until we get to dealing with the slopes for those two lines, and that's where we separate. So we have our x value, x equals pi. We need our y value, which would be secant of pi, which, keep in mind, is just 1 over cosine of pi, or negative 1. So we know the point that we are working with for both of our lines will be pi, comma, negative 1 for our tangent slash normal point. And now in order to get the slopes for our two lines, we're going to need y prime. So y prime, derivative of secant, is secant tangent. Keep in mind, we do keep track of our inside function. In this case, it was x. It's really a times 1 for derivative of that x function that's on the inside. In this example, I'm not going to write it because that's something we should work on getting used to. Y prime evaluated at pi, work with secant of pi times tangent of pi. Tangent of pi is going to equal 0, and the secant of pi, we already knew that that was negative 1. Not going to matter too much though. Y prime is going to be 0. And remember, since that is the derivative value, that is the slope of the tangent. Slope of the normal is going to be the negative of 1 over that value, which will be undefined. So the situation we are working with is one where the tangent having a slope of 0 is going to be horizontal, and its perpendicular to the normal line will be a vertical line. Hopefully remember from previous work with lines, horizontal line is always just written as y equals the y-intercept for that line, which we know from our point to be negative 1. And a vertical line is always written as x equal to the x-intercept for our line, and the x-intercept is the x value from our point, which is pi. And looking on to the final example, it says bring the pane. But honestly, it's not going to be that painful a problem if you can just keep the order straight on it. We're dealing with y equals 2x over cosecant of the quantity x squared plus pi. I would like you to go ahead and try this problem on your own. Pause the video, and when you're ready, when you think you've gotten at the very least the first step or two of this problem done, check back in. Go ahead and pause now. So looking at the initial steps that I've completed, overall, hopefully you notice that this was a quotient rule problem where we have some u function divided by some v function, and with the denominator of that function, that was a chain rule problem on its own with an outside function of cosecant and an inside of x squared plus pi. And applying the quotient rule and the chain rule where we needed to, our initial answer should have looked something like this. And finally, factoring and eliminating a cosecant factor from both numerator and denominator should yield a final answer that looks something like what you see at the bottom of your screen. So that is it for trig derivatives and Unit 3. Please make sure that you review and summarize these notes, and if you haven't already, please make sure you start preparing for your Unit 3 test. Thank you for watching.